Hello, this is Wilford Lee. Welcome to my first lecture on advanced NMR spectroscopy for Chem 374 and 964. On the screen is a title slide for the lectures, which contains my contact details, recommended text, and the copyright notice. To save the lecturing time, I would like you to read the contents therein at home, as they're only there for kind of formality. The second slide contains some important statements. The first statement says that these slides are designed to highlight the knowledge that we expect you to learn. You are strongly recommended to view the lecture videos so that you can understand the concepts and the contents, which is perhaps the most effective way to learn this topic, especially the theoretical and mathematical parts of it. I'm sure it will save you months or even years of time to learn it this way rather than learning it all by yourself. Because there is not a single book that has clearly explained all the details behind the contents we are teaching. You will also see some questions on the bottom of some slides, which are designed for you to go through at home so that you can have a better and deeper understanding of the topic. Be aware that, with a bit of variation, some of them will be put into the question bank for the final exam. Of course, this does not mean that the exam questions will be limited to those presented on these slides. This is the timetable for our NMR lectures and workshops. There will be 12 recorded lecture videos, 3 one-hour online tutorials, 1 90-minute face-to-face workshop, and 1 spectral assignment. The 12 recorded videos are equivalent to 6 hours of lectures. The reason for having 12 videos is to reduce the size of the video files so that they can be uploaded onto either YouTube or our Moodle platform without too much trouble. The 90-minute face-to-face workshop, as indicated in the table, will be conducted at 18G01 in the Chemistry Computer Room and assisted by Dr. Andrew Tague, during which there will be a 15 to 20-minute introduction of the NMR facility in 18G04, the NMR lab, by me, which is restricted to a maximum of 4 persons in the room due to the COVID distancing measures. And hence, each group has to be further divided into smaller groups to take turns. Note that, where distancing measures cannot be guaranteed, wearing face mask is always welcome and recommended. Hand sanitizer is also available on site. Anthony Fauci still warns recently that the COVID-19 pandemic is not over and another dangerous variant is possible. Besides, you are also expected to bring a laptop to the workshop with Mestri Nova installed, which is currently the best NMR processing software in the world. We have a site license for UOW chemistry, which means that you must install it on site, and it will only last 90 to 120 days. Once the license is expired, you need to reinstall it, also on site. The license file and brief installation instructions are also uploaded onto the Chem 374's Moodle or a shared OneDrive. I'm sure you are clever enough to install it, as I know that some of you have installed it last year for Chem 360. I also have a video that talks about the installation and applications of Mestri Nova last year, which can still be used as a reference. Anyhow, you're welcome to ask us any questions in the workshop. And finally, the assignment for each group has been published on Moodle and will be due on Friday of week 13, as usual. Here is a table of contents. One by one I'm going to talk about each of the topics in this list, from the fundamental theory of NMR to biomolecular NMR and NMR spectral assignment. The most important thing I like you to do is to open your mind so that you are ready to learn. As you know, our brain is somehow like a radio receiver, which can only receive information if you have the desire to learn. These topics are, by and large, about resonance. We will learn that we can only get specific NMR signals if specific conditions are met. And the condition for human learning is in fact very simple: opening your mind. Yes, NMR theory is intricate due to the involvement of quantum mechanics and experimental design. And NMR spectral analysis could be complicated and tedious. But there's nothing to stop us from understanding the wonderful idea behind the theory, the wonderful discovery, and the applications of NMR spectroscopy, which is the aim of these lectures. Let's begin with nuclear magnetism and the fundamental equation of NMR. Here, the first block of statements says that some nuclear species have an observable nuclear magnetic moment μ, which is related to nuclear angular momentum L, where gamma is a gyromagnetic ratio that varies with species. In other words, nuclei that have an even number of protons and an even number of neutrons do not have observable spin, which suggests that only the odd number of protons and/or neutrons would contribute to measurable nuclear spin. The reason is simple: even number of magnetic moments in an atom tends to pair up and cancel each other's magnetic moment. They may have very weak μ but are not observable by current techniques. Who knows? In the graph on the right-hand side, the vector L is depicted in the opposite direction of μ, simply to avoid overlapping with the vector μ, which relates to a case when gamma is negative. The second block of statements tells us the relationship between the processing frequency ω0 and the applied magnetic field B0. We often use the words process instead of spin in NMR to differentiate the nature of nuclear spinning motion from something spinning like a wheel. To understand nuclear precession or spinning, we present a nuclear magnetic moment μ with a directional vector like an arrow. This arrow precesses not like a wheel but like a stick sweeping on the surface of a cone about the cone's axis of symmetry, as shown by the dotted green line in the graph on the right. Since nuclear precession is very, very fast, the time average of the precessing vector μ is effectively its z component μz. As any transverse components μx and μy are always cancelled by their opposite components during each cycle of precession. Also, by convention, its angular frequency is presented as a vector, denoted here by ω0 on the z-axis. How fast does the μ precess? For 1 H proton, it is about 2,500 cycles per second in the Earth's magnetic field. And, in an NMR experiment, it is a few 100 million cycles per second. In fact, every 1 H proton in our body spins in the same way under the effect of the Earth's magnetic field, but we never feel it. The first statement in the second block is about what a magnetic moment μ will experience in an external magnetic field, which can either be one that exists naturally, like the Earth field, or one that is applied on purpose to excite nuclear spins, like a magnet. It's easy to imagine that, under the effect of a uniform external field, like an external magnetic field for a spinning proton or the gravitational field for a spinning top, a spinning object tends to be aligned by a precession torque about the axis of spinning, causing it to precess about an axis on a conical surface, as shown in the top graphs. The fundamental equation tells us how the angular frequency of a nuclear spin relates to the strength of a static external magnetic field, which can also be presented in a vector format by changing the omega-naught and B-naught to boldface. In which case, it is a vector equation, there's no unit involved. Note that B-naught is external to mu, is static, and is strong. Here is a short list of some gyromagnetic ratios. The first two lines are 1h in different units, and they are equivalent. Keep an eye on the gamma for 15N, which is negative. In other words, 15N nuclei precess in the reverse direction from 1h's. It is also useful to remember that the gamma of 13C is about a quarter of that of 1h's. And, for 15N, it is about 1/10. The grades of NMR spectrometers are usually indicated by the NMR frequency of 1h in megahertz. For example, Bruker 900, Bruker 500, Varian 500, Joule 500, etc. With this, the strength of the magnet can then be worked out approximately, as shown in the example. The formula here is simply a rearrangement of the fundamental equation. Knowing the strength of a magnet, you can also work out the NMR frequencies of different species in each of the magnets. For example, 13C in a 500 MHz spectrometer will spin at around 125 MHz. As the gamma of it is about a quarter of that for 1h's. At the bottom of the slide is the first question for you to try at home. Now we want to talk about local magnetic field, i.e., B local, which is a fraction of B0. It is also external to mu, is weak, and is contributed by nuclei and electrons surrounding it. Different catalogs of particles affect the local magnetic field differently. Surrounding diamagnetic nuclei tend to align oppositely to mu, weaken the field, and hence shield the mu from B0. Surrounding paramagnetic nuclei, on the other hand, affect the external field differently. They tend to align with mu, enhance the field, and hence to shield the mu from B0. The electron density also affects the local magnetic field in some way. An increase of surrounding electron density shields the mu and shields it otherwise. For example, the presence of an electron withdrawing element such as oxygen in the immediate neighbor decreases the electron density surrounding a mu, and hence shields it from B0. The total strength of local magnetic field is just a tiny fraction of B0 and is associated with the total shielding constant, sigma. When sigma is positive, it is a shielding factor. When it is negative, is a de-shielding factor. The effective external magnetic field B effect then becomes slightly different from the prime field B0. With the presence of the effective magnetic field, the NMR frequency of the individual nucleus gets changed, and it is denoted here by capital omega with a subscript J. The change, though small, is significant in high-field NMR, and it's fundamentally important in NMR spectroscopy. A change of resonance frequency in NMR spectra is called a chemical shift. This slide is about chemical shift. The first statement simply says that a chemical shift represents a shift of an NMR frequency Vj from that of a zero reference V0 reference. In the two mathematics expressions, the denominators are the same, being 1/1,000,000 of V0, which is why the unit is ppm, which means parts per million of V0. It is there to rescale the shift so that it is more readable, is dimensionless, and is independent on the spectrometer used. Equation 2 is a general equation for a chemical shift that is not referenced to a zero reference, where delta ref is the reference's chemical shift. For example, the conventional 7.26 ppm of the residual CHCl3 in 99.8% CdCl3 from the zero reference TMS. Note that, in equation 2, the reference can also be a zero reference. Apparently, it becomes equation 1 if the reference is a zero ref, because the delta of a zero reference is 0 ppm. This is a recap of what you might have learned, but with a little more explanation of concepts so that you understand a bit more on NMR spectra. The slide uses a 1D NMR spectrum as an example. The nuclei on the left of the spectrum are shielded from B0 by their local magnetic field, and those on the right are shielded. We only need to remember the terms used on one side, say, those on the right, as the terms on the other side are just the opposite of them. For example, shielded is changed to shielded on the left-hand side. And lower NMR frequency to higher NMR frequency, upfield to downfield, diamagnetic shifts to paramagnetic shifts, etc. There are a few more concepts that are useful for us to learn. The first concept is transmitter frequency. It is the precise pulsing frequency in an NMR experiment to resonate the nuclei, which is in the order of megahertz. This is like the megahertz or gigahertz carrier frequency in radio signal transmission technique, which carries 20 to 20,000 Hz sound to a distance. Digital NMR time domain data, however, contains only modulated or filtered low-frequency digital signals, say, within 10,000 Hz for 1H NMR spectra. It is created by deducting the V0 frequency, 500 MHz for example, from the actual NMR frequency received, which is usually in the range of V0 frequency plus minus 5000 Hz for 1H NMR. So that the spectral resolution is improved to a level that can be easily viewed by human eyes. This is like converting the very high radio frequencies in the sky to audio frequencies that we can hear. Strictly speaking, this is very important to understand. The frequencies presented in NMR spectra are not the resonance frequency but the filtered or reduced NMR frequency. The nuclear magnetic resonance frequency is in megahertz, whereas the latter, what we save and view in NMR spectra, is in 1000 Hz. Another concept is transmitter offset, which is a shift of the transmitter frequency from V0 in an experiment so that, after a Fourier transformation, the NMR spectrum is approximately centered about the midpoint of a spectrum, where the dashed line is. In summary, we have talked about the fundamental equation of NMR frequency in the presence of a local magnetic field, and NMR chemical shift. The first one implies that nuclei with observable spin will precess in an applied magnetic field. The second one tells the effect of a local magnetic field, which changes the NMR frequency of local individuals. And the third one tells us the meaning of chemical shift. We also have explained some concepts of NMR spectral frequencies in detail. The example here explains the meaning of ppm in NMR, which indicated the shift of frequency from a zero reference in parts per millionth of V0, and hence it is independent on field strains. This concludes our first NMR lecture.